Hello physics students, this is Dr. Brinzy here, and this is the video for lesson 5.1.4. And this lesson is going to be about, our objective here is that we're going to be able to explain why a tether ball revolves in a larger circle when it's going fast. But, as I was going through this, the math was just so complicated. And I wouldn't say so complicated. Some of you might catch on to it. But it involved a lot of math. I thought it was going to be easier than it actually was. So, we're not going to actually be able to explain why a tether ball revolves in a larger circle when it's going fast. We're just going to talk about how tether balls work and be able to calculate certain aspects of its motion, its circular motion especially. So, with that said, now a tether ball, if you've ever played the game, is an example of what we in physics call a conical pendulum. So the way a conical pendulum works is that you have something on a string, like a tether ball, and the way this works is that this tether ball is going to go around in a horizontal loop. And it's going to go with some sort of circular radius r. And let's show, first of all, that this actually can be uniform circular motion. So this tether ball is going to move, like I said, with a velocity v, tangential to our horizontal circle. So if you were to draw a free body diagram of our tether ball or any other conical pendulum, what you'd find is the tension force goes up along the string, which makes sense, and we would have a gravitational force, m times g, acting on the tether ball. And those are the only two forces acting on this tether ball. No other forces are acting on it. So what causes our centripetal acceleration around this center right here? Well, it turns out when you break down the tension force into its horizontal and vertical components, well, the vertical component is going to balance out m times g because it's not going to be accelerating up or down. And it turns out that the horizontal component of our tension is going to provide the centripetal acceleration that will allow our tether ball to go in a horizontal circle. So what do those formulas look like? Well, we have to separate the horizontal and vertical directions, just like we did when we dealt with two-dimensional force problems. So we're going to set up our two axes. We're going to call the y the vertical axis and x the horizontal. And we're going to set up F net equals ma, Newton's second law. And we're going to look at the two directions separately. So let's look at the horizontal direction first. So in the horizontal direction, I have t sine theta equals mass times centripetal acceleration. And if I substitute v squared over r, I get t sine theta equals mv squared over r. And by the way, T is the tension force here. I just wanted to be consistent with the diagram there. So let's look at the y direction now. In the y direction, we have T cosine theta minus mg equals 0. Why did I put 0? Because the tether ball is not going to accelerate up or down when it is going around in a horizontal circle. So we can actually set t cosine theta equal to mg by adding mg to both sides of this equation. Now, I think for the purposes of tomorrow, this is about as far as we're going to need to go. But those of you who want to stick around and want to get ready for some really crazy, I wouldn't say crazy math, but it's going to involve a lot of thinking. So I'm actually going to try to show you that you can prove that the faster this tether ball goes, the larger this radius has to be. And it involves a little bit of creative thinking with math. Now the first part of it, oh, and by the way, I should say that at this point, if you just want to cut off your notes at this point, I'm okay with that. You don't need to take notes further on from here, but if you're really curious about proving that this tether ball will actually have a larger radius when it's going faster, stick around, but you don't need to take notes. Alright, so let's bring on those same two equations that we ended with. And let me erase that little g up at the top. So these are the two equations we stopped with. Now, let's take this equation and divide it by this equation. Oops, I forgot to draw my triangle here just to remind us. And an additional thing here is that I define this height h here, just so I had something to put there. It didn't say that, it didn't show that in the original diagram, but you'll see it'll come into use here. So I'm going to take this equation, divide it by that equation, and it turns out when I do that, and I do a little simplifying, the t's divide out on the left side, the m's divide out on the right side. So our result's not going to depend on the tension force in the string, and it's not going to depend on the mass that's hung on the end of the string, which is interesting. Well, sine theta over cosine theta equals tangent theta. So I have tangent theta equals v squared over g times r. And it turns out that tangent theta is opposite over adjacent, so that's r divided by h. So I get this when I divide, when I multiply both sides by, or cross multiply, I actually went and cross multiplied here. I get g r squared equals h times v squared. Well, that's not too informative because I really don't know what this h is going to be. I do know what the length is going to be. I mean, the length of the tether ball rope is going to be something that I can measure, but I can't really measure this height necessarily. So I want to get rid of this h. And in order to get rid of this h, I have to bring in another equation, and that is Pythagorean's theorem. So I'm going to let h equal the square root of L squared minus R squared. That just comes from Pythagorean's theorem. And we'll replace h in this formula right here with this expression. And when I do that, I get g r squared equals v squared times the square root of L squared minus R squared. Alright. Well, that doesn't give me any information about how velocity is related to radius. If I solve for velocity squared by dividing both sides by this square root, I get something that looks like this. gr squared divided by the square root of L squared minus R squared. Wow. Okay. Now this is where life gets interesting mathematically. I'm going to do something that's called parameterization. In other words, I am going to define a new variable. I'm going to say x equals r divided by L. Okay. Which means that r equals L times x. Now you might be thinking, Dr. Brinsley, why in the world are you doing this? It'll actually become clear in the end, but for now, stick with me and I'll show you why parameterization is so useful. So, when I replace all my r's with L times x, I end up with something that even looks worse. But what I noticed in my radical sign down here is I have L squared minus L squared times something, so I can factor out L squared, or actually the square root of L squared, down in the denominator. So when I do that, well, what's the square root of L squared? That's just L. So now I have V squared equals G times L times this function here. Okay. Now, that doesn't look too informative, does it? But what I can do is I can actually plot this thing. And let me show you. When I plot this on a graph, I get something that looks like this. So why would I care to plot? Why would I care to plot? Well, actually, let me write it down again. Why would I care to plot this thing right here? Well, because that thing tells me what v squared divided by g times L is. So if I plot this versus x, what I'm doing is I'm plotting v squared over g times L. Well, g and L are just constants. Those just depend on, the length of my cord and the gravitational constant. So really what this is that this is a kind of a measure of v squared. And then x is radius over length. Again, this is kind of like a measure of the radius of the circle. So, when I plot this as a function of x, what I'm doing is I'm plotting v squared over gl versus r divided by l, radius divided by length, this value x. So how can that be helpful? Well, I know that if velocity increases, then this thing increases. So I know that as I go higher on this graph, velocity increases. Now, if velocity increases, what's happening to my radius? Well, initially, it's getting larger at a pretty rapid rate, but then as I try to spin this faster and faster, what happens is that it starts getting up to a certain height, and then it's starting to not gain much radius when I add more and more velocity. So it's almost like you have to read this thing sideways. Instead of reading it as y versus x, you almost have to read it as x versus y. So what this graph definitely shows me is that as velocity increases, the radius increases as well. So I've just shown you that on a tether ball, if you spin the ball faster, the radius of the tether ball definitely has to increase. All right, well, that was definitely a little bit more than what what I think would be expected for you to handle. Again, what I think you guys would be expected to handle is stuff like this right here. I don't think you would need to go farther than that. And you'll probably be given things like, the tension in the rope and have to figure out the angle and the radius or something like that. So this is probably our foundation for tomorrow, but I thought it would be fun just to show you that, yeah, radius definitely increases as velocity does. And I know the math was complicated. I don't expect 100% of you to understand it, but I just put it out there for the curious. Okay, ladies and gents, I look forward to seeing you in class, and I'll talk to you soon. Bye.